So I'm sitting here in the lab watching three big fools trying to finish up their unknowns piece. Can you guess who they are? Yep, you guessed it. The biggest three fools in all classes. Oh, actually, it's remarkable. It's all C block people. Huh. That is kind of weird. All right, so we're going to be talking about two things. The first is neutralization reactions, and the second will be how to calculate pH. I'm sure you guys have all heard of the term pH before, and you know that a pH of 7 means that something is neutral. And from yesterday's quote-unquote screencast that we did in class, you are going to use some of that information with the self-ionization of water and Kw to help you understand the concept of pH. All right, neutralization reactions first. Here I have a beaker that contains a solution of hydrochloric acid, so it's in water. And if you recall, way back at the outset of this set of topics, I talked about litmus paper. Well, you should know that an acid will turn blue litmus paper to red, indicating indeed that it is an acid. And here I have a beaker of base, also in an aqueous solution form, and it's a strong base. Looking above, the hydrochloric acid is a strong acid, and I have a strong base here. And with regard to bases, it takes litmus paper and turns red litmus paper to blue. Now the other thing I want to add here is that I want you to imagine that these are both 1 molar solutions. So I'm going to have a mole of hydrogen or hydronium ions floating around in solution because the HCl fully dissociates. And I'm going to have a mole of hydroxide ions in my NaOH because NaOH fully dissociates as well. So what would happen if I combined these two solutions, these two 1 molar solutions, one being a strong acid, the other being a strong base, together into a larger beaker? Lenny keeps bugging me. All right, so in this case, when I combine these two things, if I were to put blue litmus paper and red litmus paper into the solution, it would actually make no change. So red would stay red and blue would remain blue. And that would indicate that this is a neutral solution, or the solution has been neutralized. So to understand what's going on here, let's look at the chemical reaction that's involved in combining the hydrochloric acid and the sodium hydroxide. So there are my two reactants that I have involved. And don't forget, again, I want to remind you that in this case, I have 1 molar solutions of each. And when this, since these things are going to completely ionize, I'm going to blow this up and make it sort of like a complete ionic equation for the next line. So this is still showing the reactants, but I've just exploded them apart so that you can see that they've ionized into their individual ion components. And let's see what happens then in the reaction, what happens to the products. And for this, I want you to note here that I've formed water, and the water forms when I combine the proton here and the hydroxide here to create H2O, and then I also form salt, as you can see right here, which is the combination of the Na plus and the Cl minus. Now, you should keep in mind that as soon as that NaCl forms, it actually does break up into its individual sodium and chloride ion parts. So what you essentially create is salt water. And if you're creating salt water, you're creating a neutral reaction. What's very important for you to understand here is if I have 1 molar solutions of each one of these things, that it's essentially like me putting a 1 in front of each one of these, right? And so that means I have exactly 1 mole of hydrogen combining with, or protons, hydrogen ions, combining with 1 mole of the hydroxide ions to form 1 mole of water. If I didn't have that, let's say I had a situation instead where I didn't have 1 mole of sodium hydroxide, but instead I had 2 moles of sodium hydroxide. If that were the case, then I'd have twice the number of moles of hydroxide ions as compared to the hydrogen ions. And if I have a 2 in that place, I think you can see that I'm going to have leftover hydroxide ions in the end, which would not make this a neutral solution. It would make it a basic solution. So in order to have neutralization, not only do you need to have an acid and a base come together, but the concentration of the hydrogen ions and the hydroxide ions must be the same in order for the neutralization to take place. What color did you say that was, Will Van Dam of the River?
This?
Yeah, because you, no, the other one. Spin it.
This is the iodine test.
Oh, okay, sorry.
Yeah. Check. See you. No.
Now there are other neutralization reactions that we can do. Let's say that we have hydrochloric acid again as our strong acid, and we combine that with potassium hydroxide, which is a strong base. Take a moment to figure out what forms as a result of this neutralization reaction, assuming that we have equal concentrations of the hydrochloric acid and the potassium hydroxide. And then I want you to do the same for this one. Imagine we have sulfuric acid, H2SO4, and we combine that with magnesium hydroxide, also aqueous. I want you to tell me what that forms. I got to move this down slightly so it gets out of the way. All right, so take a moment to put the pause on and try to complete these reactions. All right, so there you go. I'm sure that the answers I have right here in red are the answers you got. If not, you probably need to ask me some questions. And once again, we have the idea here that you form salt water because KCl is going to dissolve in the water, forming salt water, and so will the magnesium sulfate dissolve into the water that's formed here. The one thing I do want to point out to you, however, is notice here that the sulfuric acid, the H2SO4, there are two hydrogen ions that come off when it dissociates, when it ionizes. And over here, you can see there are going to be two hydroxide ions that come off and dissociate. We actually refer to when you have something that will dissociate into two protons, we call that a diprotic acid versus a monoprotic acid, which is what you would see with HCl. There's also something called a triprotic acid, which would be something like H3PO4, would be phosphoric acid, a triprotic acid. All right. Let's move on to the concept of how to calculate pH. I know that you probably from your sixth grade science classes know that pH is a measure of something being an acid or a base. And you know that if you have a low pH, which means, say, a number from 1 to 6, or actually, you could even have a number of 0. So let me put that there. You could go from 0 up to 6. Actually, let's see. Can you have a pH of 0? Now I can't remember. Hadley, can you have a pH of 0? Maybe you can't. I have to look into this. Anyway, let me go back and erase that. When I stop and think about it, it doesn't sound right. I think you can only have a pH of 1 up to 6, and then that would be an acid. And if you have a high pH, that would be from 8 up to 14, and that would be considered a base. And then when you have a pH of 7, that means it's neutral, meaning there are an equal number of hydroxide and hydronium ions in the solution that you're testing. So what is actually the pH? What does it mean? And first thing you should know is that in English, pH means the power of hydrogen. And when I say the power of hydrogen, what I'm really saying, it's the power of the protons or the hydronium ions. So it's really more accurate to call it the power of hydronium, but that's not what it is. It's the power of hydrogen. So you also could calculate the pOH of something if you wanted to look at the power of the hydroxide, but we're not going to do that. We're just going to stick with pH. And in terms of calculating the pH, you would take the minus log of the concentration of the hydronium ions that you have in the solution. So this is actually something that you might need to teach yourself how to do on a calculator. Hold on, let me take a look at a graphing calculator. Okay, so let's say I give you a really easy question, such as a sample of my blood has a hydronium concentration of, 3.72 times 10 to the minus 8, and I want to know what the pH of my blood is. So don't forget this. This is going to be important. Let's go over here and take a look at Will Van Down by the River's calculator here so I can tell you how to do this. So the first thing you need to do to tap this thing in is hit the minus sign, which is the fella in, oh, it must be right here. So you hit that thing. Actually, I better be sure this is true. Hold on, everybody. Hadley's bugging me, so I have to stop. Okay, so I was so rudely interrupted by Haddles. Now I can't remember. Okay, so you hit the negative sign here in parentheses, and then you hit the log button right here. And then you're going to type in the number 3.72. And then you need to hit the second function, and then the double E. Where the heck is it? Oh, there it is. This double E button here, so it's the comma, I suppose. And then you're going to raise it to the -8, so you got to put in another minus sign, and then the 8, and then close the parentheses, and then hit enter. And you can see that the number you get will read out right here on the screen in giant letters 7.429. All right, and since there are only 3 sig figs to this, it's 7.43 is the pH. So you see my blood is slightly basic at that point. Okay? So let's look at a slightly harder question. Okay, I want you to imagine that the pH of pickles, all right, we want to figure out what the pH of pickles is, and I tell you that the concentration of the hydroxide ions is 1.6 times 10 to the -10. All right, and you need to tell me if the pickles are acidic, neutral, or basic. So this is a little bit tricky. It goes back to what we did in class the other day, where we use something called the KW. And don't forget, KW is 1.0 times 10 to the -14. And what that represents is the concentration of hydronium ions and the concentration of hydroxide ions in a solution that contains water. Now, that would be what it is if it was just water by itself, but it may be a little hard to follow here. If I know how many hydroxide ions that I have, I can figure out the number of hydronium ions that I have simply by plugging all this into this equation. Let me go ahead and erase this. So what I want to do is set this equal to 1.0 times 10 to the -14. But I'm going to take this number here and put it into there and then solve for this fella right here. All right, so when you do that very complex math, you're going to find that it leads to you having a concentration of the hydronium ions that is 6.25 times 10 to the -5, and that's again using the KW expression that we have there. And then when you plug this into the calculator in the same way that we just figured out how to do the pH in the previous problem, you find out that when this is the concentration of your hydronium ion, that your pH, it represents a pH of 4.20, and if it's a pH of 4.20, then it's less than, not inclusive of 7, so it is an acid. Got it? Now what if we were to do the opposite? I think I have enough time to do this. What if I gave you that the pH of something was 6.7? Could you tell me what the concentration of my hydronium ions is if it has a pH of 6.7? See if you can work that out. So hit pause, no cheating. Okay, so I'm actually not going to give you the answer yet because I think you cheated and didn't pause. So pause, you jerky, and try to figure this out on your own. All right, now I'll tell you. So the opposite of doing the log is that you need to raise something. It's 10 raised to some power. So in this case, it's going to be 10 raised to the -6.7. Oh, geez, why did I do that? Where's the undo? 0.7 here. So when you put that into your calculator, oh boy, Where's that? Where's the calculator? Hey, here we go. Here we go. All right. So if I do this, if you look at your calculator, there it is, happiness. Do you see above the log button, you see a 10 raised to the x? So you're going to have to hit your second button, which will give you 10 raised to the x. And then you're going to put in the number, or you have to hit the minus sign here, and then 6.7, and hit enter. And you can see the number you get is not the number that I have here. Get rid of that pile of dung. You should get the number 1. Actually, you're rounding this properly. It's 2.00 times 10 to the minus 7. And again, that is the concentration of your hydronium ions in this particular situation, and that is what? I don't remember what I was talking about. Anyway, there you go. Bye.